When we broke for intermission, we had talked a lot about wrought iron and cast iron and how they went from being relatively expensive artisanal materials that were used for building components, stretching out and becoming more of a system. So columns and girders. And in the last little bit here, we'll talk about the sort of last few moves where the mill construction that starts in the British mills ends up sort of taking over and creating whole buildings on its own. One sort of intermediate stop, though, is this library in Paris by French architect Henri Labrouste. This is an example, really, of a kind of engineering application of iron construction in an architectural setting. And you can see the sort of struggle to match the traditional forms that are still very popular, French neoclassicism, Roman arches, and rigorous order. The Greco-Gothic, remember we talked about that combination of Roman order and Gothic lightness. And here you see it, I think, very much like that church in Liverpool that we looked at briefly, trying to merge the modern material with the classical style. Here, the Bibliothèque Sainte-Geneviève, it's actually right across the street from Sainte-Geneviève, the church, now the Pantheon, Soufflot's Greco-Gothic masterpiece. And you can see it's almost like the iron has had time to come out of the stonework here. There's heavy stone walls surrounding the outside, which give it its kind of architectural character. But then on the inside, you get this very, very lightweight, yet still very kind of classical feeling. And that merging again of lightweight structure with a kind of rigorous classical order is one of these places where architecture and engineering start bumping up against each other pretty productively. Now, the emergence of iron as a wholesale system, in other words, taking up not only the structure, but also, as we'll see, the cladding, really gets its start in New York with cast iron storefronts that begin to emerge out of industrial ironworks in the 1830s. The first one is the J.L. Mott foundry, which makes basically kind of mullion systems and things for single floor storefronts in 1835. He combines this with cast iron structure, so columns, in 1840. There are two people who sort of show up to New York in the 1840s. Daniel Badger, who has an iron storefront business similar to Mott's, comes to New York in 1842, and James Bogartis opens a cast iron factory in 1848. Badger and Bogartis end up teaming up. They take the storefront business, basically combine it with the mass production of cast iron, and begin producing basically prefabricated buildings. William Fairbairn had foreseen this in 1840. The British engineer and scientist who developed really the science of the I-beam, thought that iron could sort of get out of the structural cage and form the exterior of the building as well. It's fire resistant, and so it's as good as brick in some ways, but of course iron is much, much lighter than masonry. So you're putting less load on the foundations, you're putting less load on the columns in the lower floors. There's a lot to like about a very, very lightweight material that goes not only into the structure but also into the cladding. On the left, you see Fairbairn's perspective of what he thought an all-iron building could look like. You might notice the dots that indicate rivets or bolts on the exterior. And on the right, a typical section. His idea was that you would take cast iron columns, you would embed wrought iron beams in a concrete matrix to fireproof them, but also to give a durable floor. And that concrete would be poured against an iron formwork. That curved line represents the formwork that the iron would be poured against. Fairbairn never built this, but it's very much in the air in Britain and, of course, in America, that this new material, as it gets cheaper and cheaper, can start to be used for more and more in building. Badger and Bogartis begin selling their storefronts in 1848 in their cast iron structure, and they begin to produce these catalogs where they prefabricate these cast iron elements by the dozens, and they don't do them for specific buildings, but they literally do them as a kind of warehousing exercise. So you can go to Badger and Bogartis and buy a kind of ready-made building, right, that can be put on carts, taken to your site in Lower Manhattan and basically bolted together. And you can see that there's a great deal of skill involved in the cast iron that Bogartis brought to the enterprise. On the right are details where you see the rich, in this case, classical ornament, or kind of classical-esque, right? The proportions are all much more those of an iron structure than of the classical columns that they're trying to imitate. But if you look at the sections, you can see that these seemingly very heavy masonry-like elements are actually composed of very, very thin, looks like sort of folded cast iron. Of course, it's not folded, it's cast, but you can imagine the skill necessary to get a piece that thin made between two molds in and out of the mold and sized properly when it finishes cooling. So there's an awful lot of very beautiful detail. This is, of course, a super robust material. You see on the left the sense that this is being produced just constantly, right? So there's a mass production process that makes it very quick. And if you look at the storefronts in the middle, there is almost a kind of accidental Greco-Gothic that happens in these cast iron storefronts. The choice of classical ornament is intentional, right? That's very much the kind of style at the time. Greek revival is big in the United States, and this is an attempt to sort of equal that. But the issue is that the windows, of course, need to be very large because there's no electricity yet. So you need as much daylight as you can get in. And that basically slims the proportions down, right? Trying to make big windows makes for very, very narrow structure. And cast iron is, of course, perfectly suited to this. So once again, we get the order from the Greco-Roman tradition, the classical tradition, and we get this very, very light sensibility that's almost Gothic in proportions. Bogartis writes a well-known essay on cast iron buildings in 1856, and it's interesting to look at the rationale he gives for building in cast iron because it follows very closely the kind of basis of the course. He says that when you've bolted everything together, all of these individual elements, because you can tightly attach them to one another, form one stable whole equivalent in strength to a single piece of cast iron. We'll see that that's not actually the case when we talk about skyscrapers in a couple of weeks, but it's close enough, right? More so maybe than some of the looser timber construction that's going on around them. Such a building may be erected with extraordinary facility at all seasons of the year. It's very simple to just bolt the pieces together. You don't need to keep things perfectly straight. That the cast iron takes care of itself. No plumb is needed. As fast as the pieces can be handled, they can be adjusted and secured by the most ignorant workman. Now, that, of course, sounds pejorative, but what Bogartis is saying is that you can ship the stuff to the site just in time, right? It's sitting in the warehouse ready to go. And as the pieces arrive, you don't need skilled labor. You don't need craftsmen to put it together. It's not an artisanal process. It's a factory process. But the factory is actually happening both in the factory, but also on the job site, right? You have unskilled labor that's able to just bolt these pieces together. They can be exported. Bogartis builds cast iron buildings as far west as Chicago, and its happy adaptability to ornament and decoration, that you can get a huge array of styles taken care of because the process is so flexible. And Bogartis' skill at making the molds that the cast iron is going to fit in is so great that he can basically make like whatever style you want. Ornamental architecture, which with our limited means is apt to be tawdry because incomplete, thus becomes practicable. You can make much more complicated ornament in this casting process than you could if you were budget strapped but trying to make a hand-carved building. And these are some examples of Badger and Bogartis' storefronts. There's still lots of these left in Soho and in Lower Manhattan in New York, and they are kind of accidental architecture. The mass production means that there's a lot of repetition, a lot of sort of sameness. The need for light means that there's a slenderness, a thinness, and you can see the array, the range of ornamental possibilities, though most of them at the time, just because of stylistic preferences, ended up being fairly classical. That emphasis on sameness, on repetition, comes, of course, from wanting to use one mold as many times as you can. But you can see that it begins to create its kind of own aesthetic, right? That multiple repetition goes to the idea of order, this kind of rich order, and a kind of grain, a horizontal and vertical grain to the facades that visually is quite successful. Now, one of the most kind of telling projects that they have is the Harper's building for the magazine in 1854, and this is an all iron structure with cast iron columns, wrought iron girders. You can see that there are still brick floor arches for fireproofing, but the facade of the building is all cast iron as well. And this Badger and Bogartis cell is an all iron building, right? There's no timber, there's just the brick floor arches. They are manufacturing every piece of the structure and cladding and shipping it out to the site. This building in particular is highly influential. It's got offices, it's got sort of factory loft spaces, and it has workspace also even in the basement. And you can see too that it's very, very lightweight, right? It sits very lightly on the ground, just has a very, very slim foundation pad that it sits on. So it's incredibly cheap as well. Fast to put up, cheap to put up, and a hugely functional, very, very open set of floor plans with these tiny, tiny columns that let you move your equipment and your people around wherever you like. Probably their best known building is the Hofwatz store in 1857. This was a retail establishment in what's now Soho. And not only is it a particularly fine kind of ornamental facade, you can maybe vaguely see reflections of the Colosseum in the detail, but it also combined cast iron facade, cast iron structure, and one of the first steam-powered passenger elevators. So a building that really kind of encapsulates a number of advances that are all going to be critical to the modern skyscraper in 20 or 30 years, 2 or 3 lectures down the road. Bogartis and Badger also make towers out of cast iron, and here things get really interesting because the lower cast iron stores that they build are generally self-braced. In other words, they're only 4 or 5 stories. They're a little bit rickety, but they'll stand up in the wind. Here you see them trying to give these towers. On the left, a shot tower. They drop molten lead from the top, and you get, as it coalesces and cools, falling down the tower, you get shotgun pellets. And then the one in the center and on the right, these are both fire towers, watchtowers that would go up on hills in New York so that firemen could watch for smoke on the horizon. And you can see that the shot tower is no problem, right? That's easy to brace because it's got masonry infill between all of this cast iron structure. The fire towers, on the other hand, have the problem of standing up in the wind and also not rotating, right? Not experiencing torsion. And you can see Bogartis experimenting both with moment frames, so very, very stiff connections. Just try to make the connections between the columns and the beams as tight as you can. And on the right, you also start to see cross bracing, wrought iron cross bracing, particularly in the upper story, that's going to prevent the tower from essentially rotating down. These are all very difficult to do, though, in cast iron because the material is so imprecise and because it can't be drilled or cut after it comes out. All of the connections in these are relatively loose. And Bogartis has to struggle with things like shims and packing to get the tight connections necessary to keep these things up in a windstorm. Now, at about the same time, Peter Cooper is working has his own iron foundry, and he comes up with a series of structural shapes and with a building system that kind of rivals, maybe even goes beyond Badger and Bogartis's. Cooper is the Cooper of Cooper Union. When he builds that building, he uses his own iron production to structure it. On the left, you see what he called a compound beam, which is approaching a W shape using 2 slightly easier to roll channels, left and right. This is Cooper and Hewitt kind of trying to catch up with the work that Fairbairn and Hodgkinson are doing. It's not that they don't know that the I-beam is the better shape, it's that they have trouble rolling that detailed a shape. And so channels are easier. They make this compound beam by riveting 2 channels together. You see a detail of a typical floor arch with the bricks in the middle. And then on the right, their full system, which as you can see takes advantage of railroad iron, but also uses cast iron columns, wrought iron girders, and then again those brick floor arches for fireproofing. This happens abroad as well. This is a building a chocolate factory over a river just outside of Paris, built in the 1870s. And you can see here it's a plaster and brick facade, probably enough to resist the wind on its own. But the builders here have also installed all of this diagonal bracing out of iron. And that both carries the floor loads and it provides wind resistance. The interesting thing about this, though, is that they've chosen to expose it on the exterior. This is probably as fancy a factory as you'd ever see, right? It is much more architectural than a lot of the industrial structures that we've looked at so far. But they've made the structure really a part of, not just a part of, they made the structure actually the organizing principle of the facade on the outside. And we'll see this again and again too, that the structure, because the structure wants to be regular, it wants to be orderly, this has an impact on the way that the exterior of the building is seen as well. So all of these projects have had to balance the performance of cast iron with its lack of tensile strength and its lack of workability. Or they've had to balance the tensile strength of wrought iron and its ductility with the expense of having workers actually puddling the carbon out of the iron. The answer to the problem, of course, is a material that would be both inexpensive to make, that would be good in compression and good in tension, and that could be cut and drilled and shaped very precisely. And steel was this material. It had been known about for centuries, if not millennia. The kind of magic formula for steel is that it has a very, very precise carbon content of less than 1%, between a tenth of a percent and 1%. That's a very, very difficult sort of precision to hit. If you're trying to scrape carbon out of a pot of molten iron, you're very unlikely to hit exactly that number, right? You basically what's happening in wrought iron is you're taking out absolutely as much carbon as you can. Steel is therefore an extremely expensive material. It's artisanally not just fabricated, but it has to be artisanally produced, right, by someone who really knows what they're doing. In the 1850s, an Englishman named Henry Bessemer realizes that if you introduce even more air into the molten iron than the bellows are creating in typical blast furnaces, you can actually take out all of the carbon very easily. The oxygen in the air binds with the carbon to form carbon monoxide. That gets released through the heat of the reaction, and once all the carbon is gone, you have this very, very pure iron ore. That's great, except that with no carbon at all, the steel is quite weak. You can, however, put the carbon back in very precise quantities. So the trick to Bessemer steel is to blow air through the blast furnace, take out all of the carbon to make molten, very, very weak steel, and then to very precisely add carbon back in until you get to that 0.1 to 1%. The result is a material that's elastic and ductile, right? It's very, very easy to work, strong in compression, strong in tension, and it can also be alloyed. You can add other metals to the ore while it's being melted to adjust the properties of the iron. Bessemer is the first one to commercially do this. Siemens Martin, which is a German process, comes along and does something similar in 1870. Rolling of steel takes from wrought iron technology, adjusts it to the peculiar material properties of steel, and within a few years after Bessemer's process comes online, rolling processes are there to make beams out of steel in the same shape that wrought iron beams had been made in before. We'll take a look at Firth of Forth, which is the sort of proof of material for steel, the greatest application of it yet. And then by 1918, too, welding becomes another tool that you can add to the palette of steel construction. So you may have seen some of these old Bessemer converters in old films or something. They're these giant tanks that basically rotate one way or another. And the sequence here is on the top left. You take molten pig iron and you pour it into the converter. You tip the converter up. In number 2 on the bottom, you can see that they're blasting as much air into the bottom of the converter as they can. That's bubbling up through the molten iron. And as it does so, it's robbing the iron of all of its carbon molecules. The carbon monoxide gets exhausted to the top, and after that's all gone, the molten, very, very pure steel with carbon added back into it is poured back out, and it can be cooled into ingots and then rolled or fabricated. Now, very quickly, even before the Bessemer process is really commercially viable in the 1880s, the builders of the Firth of Forth Bridge take a kind of government subsidy to try out this new material. This is this colossal, about 2-mile long railroad bridge that crosses this huge river estuary just outside of Edinburgh. And you can see that there's a lot going on here structurally. It's 3 giant double cantilevers, each one built on a rock outcrop. You get the sense that you can sort of see the cantilevered ends on both sides reaching out. When we talk about bridges, we'll talk about the kind of fine grain of it and the way that the pieces all work. But you can see on the right that there are both solid compression pieces and latticed or open tension pieces. And steel, of course, being equally good in both of them. It can be used anywhere in the bridge. So it's not that there's cast iron some places, wrought iron others. This is all the same material. And remember, this is a material that just decades before had been a precious metal, right? It had been used still for cookware and weaponry, specialist applications. And here it's used for what was then one of the largest bridges, one of the biggest pieces of infrastructure on the planet. So I want to close the discussion about iron and early steel, though, with another building type that steel and iron are particularly suited to, and that is the train shed. The locomotive is a technology that inspires all kinds of infrastructural improvements and architectural improvements. And again, if you think about it, it's not only made of iron, but it also has a great need for iron. All of the rails that it runs on have to be iron. All of the bridges that it goes over kind of want to be iron. And this last kind of piece of the network, the interface between the locomotive and the city, as we'll see, begins to take advantage of iron as well. Here in a really, really early train station, you see both the kind of primitive locomotive and passenger cars unloading, and you see the problem that you have to get people off the train and into the station, and you may have to do this in inclement weather. So you would like a giant long span roof that covers the various tracks that your trains are running on with as few intermediate columns as possible, right? So that the tracks can go wherever they need to go. So it's a long span, it's covered, there's usually little enclosure, and the solution, at least initially, is to build in timber and to build trusses. As you see here, a box truss. The problem with timber, of course, is that you have sparks and fire from the locomotives, and these things are a risk to just burn down. So beginning really with some of the earliest train stations, King's Cross in 1852, iron becomes the kind of adjunct to the railroad in terms of the station. King's Cross is a really, really early iron train shed. You can see it's less than 100 years after Coalbrookdale Bridge, and it's still using really some of the same approach. A single radius so that all of the pieces can be cast into the same jigs. You can see that it's bracketed against a central masonry wall to give it stability. The cast iron, remember, is all going to be just a little bit loose. And on the right, you can see a wall that's also a buttressing wall, right? That's taking up whatever thrust there is in the base of the iron arch. That thrust isn't going to be very much because the iron arch doesn't weigh very much, but it's going to be there, right? There's going to be some horizontal force down at the base. Notice that it's really tall so that the smoke and steam and things from the engines have a place to go. They don't get trapped down by the platform. And it's glazed so that you get daylight in and you can see where you're going when you're catching your train. About 10 years later, Victoria Station, here's a case where they're using wrought iron more so than cast iron, and in particular in these lower, almost cable-like rods that are taking the shallow arch truss that's above and resolving any of the bending forces that are left in it. So this is a very, very shallow arch, so it's going to be largely in bending instead of in compression. You can see that they know to truss the arch, so that almost looks like one of Palladio's bridges from about 400 or 300 years earlier. And if you think about it, as that arch wants to sag, it wants to both push out, it wants to thrust out at the base, and it wants to go into bending, basically. So it wants to have compression at the top and tension at the bottom. That tie rod at the bottom is acting almost like the flange of the beam arch, right? So it's in tension, and it's taking up the tensile aspects of the bending load. But you can see too that it's also very cleverly tying the bases, the springing points of each arch together. So it's preventing the arch from actually thrusting out, from actually moving its supports off axis. More impressively, right next to King's Cross is St. Pancras, and this is a single span arch that is an early 3-hinged arch, where the engineers know that they don't need stiff connections at the base or even at the top. They want the arch to flex a little bit so that in a windstorm, for instance, the arch can give, it can rotate a little bit around the center and around its base. The truss arch can take a little bit of bending. And since the arch has pins at the base, any movement in the arch isn't going to try to twist the foundations out of the ground, right? The foundations are always going to experience a vertical load no matter what the wind conditions, no matter how the arch is bending. Now, you might ask, oh, well, aren't they also going to experience the thrust, right? This is a gigantic arch, very lightweight, okay, but it's a huge span. Isn't there going to be thrust at the base? And the answer is that the arch ties into the thick railway deck that you see spanning across above the foundations. And that deck actually ties the ends of the arch together and eliminates the need for heavy buttressing at the sides. We do this in America too. This is a 2-hinged arch in Broad Street Station in Philadelphia. This would have been all steel. You can see the pin connections at the base. Again, the arch can bend, it can shift a little bit, and those pin connections insulate the foundations from rotation. Combining 2-hinged arch with truss principles to lighten it even further. And you can tell where the most bending is, right? The bending here is going to be at the corners or the haunches. And you can see that the truss allows the engineers to make the arch deeper where they know that the bending moments are going to be greatest. Now, the greatest train shed of them all was what never saw trains running through it anyway. That was this giant hall of machines for the Paris Exposition in 1889. And this, like St. Pancras Station, was a 3-hinged arch. We've got very good documentation on how it was built. These are kind of drawings reconstructing the process. The other kind of brilliant thing about the 3-hinged arch is that you can build all the pieces on the ground, set the pins in place, and then use cranes to literally lift them up and attach them together at the top, right? You lift both arms of the arch, you align the pieces, you run a pin through the top, and hope it all stays. In the middle, you can see the combination of steel that forms most of the arch, rolled steel that forms most of the arch, and cast steel that forms the pin, right? So a solid steel pin on which all of this sits. Now, the Galerie des Machines is a huge success. It's the kind of biggest span, largest volume thing ever built in Europe, if not the world. But it, of course, is overshadowed by its taller brother, the Eiffel Tower. We will talk about the Eiffel Tower separately, but this image has always struck me that the Eiffel Tower, in some ways, of course, it's a more impressive engineering feat. But the long span of the Galerie des Machines and the way that those arches were built, in a lot of ways, is equally impressive, even though the sort of taller cousin gets all the press. And I think, too, there is an ideal in both of these, again, the same kind of feeling as the Greco-Gothic, right? That the Galerie des Machines has this very, very rigorous plan order that ties in not only with the structural principle of a kind of evenly spaced structure that's all flexing and carrying loads equally, but it also becomes the architecture of the building, that it's a very, very ordered building. At the same time, the builders have the kind of wisdom, the realization that the lightweight nature of the arches is also worth expressing. And you can see that they carry that aesthetic not only through the exposed truss arches that bridge the space, but also in the cladding, the curtain wall that you see enclosing the building at the end. All right, we will leave it there. We'll switch to another kind of miracle material in the next lecture when we talk about an accompaniment to iron that will form another key piece of what we think of as modern building.